Hi, we have already taken a quick look at the particular case of a portfolio with only two assets where one of them is risk-free. As it turns out, there's a lot to unpack here. Note first that it's only two assets. So if the weight in one of them, let's say the risky one is X, then the weight on the other one, let's say the risk-free asset, is 1 minus X. Recall that they have to add up to 1, these two weights. It's expected return, the weighted sum of the expected return of these two assets. Let's call it like that, where P is P for portfolio, is equal to the weight on the risky asset times the expected return of the risky asset plus the weight on the risk-free asset times the risk-free rate, the interest rate. And we know already that its standard deviation is equal to the weight on the risky asset times the standard deviation of the risky asset. Let me just use sigma here for the standard deviation of the risky asset because there's no confusion. There's only one risky asset here. Let us quickly see an example of all of this. Assume that we're going to invest a total of 10,000 and 8,000 of them are going to a risky asset, the stock of Ericsson. The weight on Ericsson is then equal to 0.8. Also, the rest is placed in the bank. The weight on the risk-free asset, in this case, is 0.2. Suppose that the expected return of the stock of Ericsson is 12% and that the standard deviation of this return is 20%. Suppose further that the interest rate is 5%. The expected return of our portfolio then is equal to the weight on Ericsson times its expected return plus the weight on the risk-free asset times the interest rate. In this example, that is 10.6%. Now, the standard deviation of the portfolio is equal to 0.8, the weight on Ericsson, which is the risky asset in this example, times 0.2, the standard deviation of this return. And this is equal, in this case, to 16%. Another example. Let us retain the same numbers of the previous example with the exception that now we invest 12,000 on the stock of Ericsson. The weight on Ericsson is then equal to 1.2. But wait, how can we do this? Well, we borrowed 2,000 at the risk-free rate. We have a negative investment of 2,000. And then the weight on the risk-free asset is equal to minus 0.2. Note that what we are doing is that we are investing all our wealth in Ericsson plus 2,000. This additional 2,000 are obtained by borrowing at the risk-free rate. The expected return of our portfolio is now equal to 13.4%, and its standard deviation is equal to 24%. This whole thing is also an example of what is known as buying the risky asset on the margin, which happens anytime that the weight on the risky asset is greater than 1. Note that by doing that, we can increase the expected return of the portfolio. However, we also increase its standard deviation. Putting all together now, we can do something extraordinary. We can factor out the weight here and plug the result back into the expression of the expected return of the portfolio. After a few steps, the result is this: a line. The equation of a line, where the intercept is the risk-free rate, the interest rate, and the slope is this ratio here, a ratio that we will be talking about quite a lot in the future. Are you freaking out? If this sounds like too complicated mathematics, do not panic. Forget about it and focus on the graphical explanation that I will present in the next slide. If we do a graph where the expected return of the portfolio is placed on the vertical axis and the standard deviation of the portfolio on the horizontal axis, we can then plot the pairs of expected return and standard deviation of the portfolio that one obtains for each specific value of the weight of the risky asset. One particular such pair is the one resulting from investing everything on the risk-free asset. That is, nothing goes to the risky asset, and the weight X is thus equal to 0. That gives that point over there. Another pair is the one resulting from investing everything on the risky asset. The weight X is, in this case, equal to 1. That gives the point over there. But as it turns out, all possible pairs that one obtains by trying different values of the weight X will fall on a straight line. Points on this part of the line correspond to weights on the risky asset between 0 and 1, and points on this part of the line result from weights on the risky asset that are greater than 1. The line is known as the capital allocation line of the risky asset. Its inclination depends on this ratio, a ratio which has in its numerator the expected return of the risky asset in excess of the interest rate, and in its denominator the standard deviation of the risky asset. The larger this ratio, the steeper will be the capital allocation line of the risky asset. More on this ratio later. This is all for now. See you soon.